This is part 4 of the series Transformations, and in this part we're going to begin by talking about a concept called symmetry. And symmetry, by definition, is a rigid motion of a geometric figure that determines a one-to-one mapping onto itself. Now we're going to look at two different types of symmetry. The first one is going to be called line symmetry. So the first thing we want to do is take a look at a couple of objects. And what we want to do is determine if these objects have some form of symmetry. That is, if there is a rigid motion that we know about so far, such that these figures can be mapped onto themselves. Well, if you take a look at this figure, if I were to draw a line through this figure in this direction, I would be able to reflect these points about that line and map that figure onto itself. That's the idea of line symmetry. And the definition of line symmetry is that a figure in a plane has line symmetry if the figure can be mapped onto itself by reflection in a given line. And that line is called the line of symmetry. And of course, a line of symmetry is a line across which a figure can be mapped onto itself by reflection. Now, can you take a look at this figure and determine how many lines can be drawn through this figure so that this figure would have line symmetry? Take a second to do that. Alright, now we should be able to do this one and this one. But what about this one? If we drew it across here, we should be able to reflect this point this way, and these 2 points would be reflected onto themselves because they'd be on the line of reflection. So this one should have 1, 2, 3, 4 lines of symmetry. And we see it does. Alright, what about this figure? This figure is a trapezoid, and it doesn't look like it would map across a line this way, because if we reflected these points up, they'd be up here, and these points would be down here. This figure would not be mapped onto itself. What about in this direction, though? And as it turns out, there would be one line of symmetry here. What about this figure? If you can imagine a line through a vertex perpendicular to the opposite side, that would certainly be a line of reflection, because this point would map across to that point and this point to this point. It would make it symmetric. So how many vertices does this object have? 1, 2, 3, 4, 5. That means it should have 5 lines of reflection. And it does. 1, 2, 3, 4, 5. Now what about the hexagon? Now this hexagon is going to be a little different. It has a line this way. It has a line through these 2 vertices, because if this line is a line of reflection, this point maps onto this one, and this point maps onto this one. And then we have that line, and that line, and that, and that. So we have quite a few here, don't we? So we have 1, 2, 3, 4, 5, 6 lines. So there's 6 lines of symmetry with the hexagon. And so that's the general idea. Let's take a look at a dynamic example of this, just to make sure we can visualize what's actually going on here. Now here we have a square, and this square is going to be shown in 3 dimensions, just so that we get a better perspective on how this thing works. Now what we want to do is put in a line of symmetry with respect to the x-axis. So there's our line of symmetry. Now what we're going to want to do is we're going to want to map this onto itself. That is, we're going to want to reflect this onto itself through a reflection on the x-axis. So let's go ahead and do that. So we can see that as we reflect it across, it maps onto itself. In case you can't see that exactly, we'll change the angle a little bit, and what's happening here is we reflect across that line and it maps onto itself. So we can see that it has symmetry in the x-axis. What about in the y-axis? So let's show that. And again, we can go ahead and rotate that. And it has symmetry there. But what about across these diagonal vertices, these non-adjacent vertices here? Let's check that one out. So we do this one first, and we can see that, yes, in fact, it does have rotation, it does have symmetry across that line. And then across the other line, and we can see that it maps onto itself. So again, changing the angle. So that's the idea. That's what we're dealing with here when we're talking about line symmetry. If the figure can be mapped onto itself by a reflection in a given line. And so we saw that this square had 4. 1, 2, 3, and 4 lines of symmetry. Now for the next logical step in our progression through transformations, we're going to look at a concept called rotation, which was alluded to in this picture here, where we were reflecting across the line, but you could see that this figure was being rotated about a certain line. So that's what we're going to do next, is look at rotations. A rotation is a transformation in which a point moves along the circumference of a circle with a center called the center of rotation through an angle called the angle of rotation. Some authors use the phrase turn a figure, but I think this is a slightly more precise definition of what a rotation is. So if we call this point P our center of rotation, we're going to rotate all the points along the circumference of a circle centered at that point P. So we would have, in this case, 3 circles, one going through A and A prime, one going through B and B prime, and a third going through C and C prime. And these points, A to A prime, B to B prime, and C to C prime, are going to move along the circumference of their respective circles. But they're going to move through an angle here, this angle, which is called the angle of rotation. So let's take a look at the definition of center of rotation. And so this is the center of rotation, and it's the point around which all points of a figure are rotated, and the angle of rotation. And so this is the angle of rotation, and it's the angle through which all the points of a figure are rotated about the center of rotation. So what we want to do now is go ahead and take a look at a dynamic example of rotations, just to make sure we understand what we're really talking about when we say rotating through an angle about a point. Here we have triangle ABC, and notice that we've created circles centered at point P. Point P is going to be our center of rotation. Now it is possible to rotate about a center of rotation other than the origin. For the sake of this course, throughout this course, we're going to use the origin as the center of rotation. Now we're going to rotate each one of these points around their respective circles. Now, for the sake of this course as well, even though it's possible to rotate through an angle of rotation of any arbitrary angle measure, we're always going to be using increments of 90-degree angle measures. And positive angle measures are generally measured counterclockwise, and negative angle measures are measured clockwise. So let's look at what happens as we rotate this triangle through 90 degrees counterclockwise. And as we rotate it, you can see that each point moves along the circumference of its respective circle. So A moved along this circle to A prime, B moved along this circle to B prime, and C moved along that circle to C prime. Now the critical factor here is, let's take a look at what's happening with these points. Now notice, through a 90-degree angle, we have that concept of perpendicularity going on again. Notice what happened. The X went to Y and the Y value went to X. The difference is that the Y value over here went to X but became negative. So we have a transformation rule. And that transformation rule was XY went to negative YX. So this is negative YX. I'm going to go ahead and write that rule down here so that we have it for reference. We said that XY goes to negative YX. Now let's use that, and let's go ahead and rotate through 180 degrees. What we're going to do, in essence, is we're going to take these points and rotate these points 90 degrees counterclockwise. So from a fundamental standpoint, we're applying two 90-degree rotations counterclockwise of 90 degrees to each one of these points. So just to take point A, we went from 6, 4. Applying this rule is negative YX. So this point would go negative 4, 6. And that's this rotation. So this is 90 degrees counterclockwise. Now if we do it again, we apply this rule to this point, we should get negative Y, which is negative 6, X, which is negative 4. And this should be 180 degrees counterclockwise. So let's rotate this through 180 degrees. And there we are. And look at point A. Negative 6, negative 4, negative 6, negative 4. Now if we did it again and rotated it 270, we'd be taking this set of points and applying this transformation yet again, which is the same as applying this transformation 3 times to our pre-image points. So there's the 1, 2, and let's do it a third time. So negative 6, negative 4 would go to negative Y, which is 4, negative 6. Negative Y, X. Negative Y, X. And that would be 270 degrees counterclockwise. And let's see that rotation. So let's go 270 degrees now. And take a look at point A. 4, negative 6. And there we have it. Now clearly if we executed this one more time, this figure would map back on top of itself. So a rotation of 360 degrees brings us back to the original. Now it's important to also note that if we went negative 90 degrees, that is clockwise 90 degrees, that clockwise rotation of 90 degrees is equivalent to a counterclockwise rotation of 270 degrees. So if we went backward and we went negative 90 degrees, we would be right back at the same set of coordinates. So rotation clockwise of 90 degrees is the same as a clockwise rotation of 270 counterclockwise. Let's go back now and summarize what we've learned. We learned that a counterclockwise rotation of 90 degrees is XY goes to negative YX. 180 is this and 270 is this. I don't recommend memorizing these. I would recommend just memorizing this and applying it however many times you need to apply it to get to the proper angle measure. That's the easiest way to do it. And then we have the clockwise equivalent to counterclockwise. In the next part, we'll work some examples, so I'll talk to you in the next part.